Thank you very much for clicking on this video. I am very happy to have you here with me. We have actually looked into bonding that exists between metals and also look into bonding that exists between non-metals. And those that exist between metals, we call them metallic bonding. Then those that exist between non-metals, we refer them as covalent bonding, where we have ordinary covalent bonding and coordinate covalent bonding. In these covalent compounds, we have some other forces that helps them to keep them together, something that look like van der Waals forces, the weakest among them. And we have dipole attraction forces that exist between them. This is actually showing us that there is an ability of one of the non-metal to act as if it is highly positive and the other remain as highly electronegative by becoming electronegative pole and the other one become a positive pole. So we call it dipole attraction moment. And if, for instance, the dipole attraction is existing between hydrogen and the highly electronegative elements that has more atoms, that is nitrogen, oxygen, or fluorine, we call that particular force hydrogen bonding. Now we are going to further this bond in order to conclude this our chemical combination by looking into metal and non-metal bonding. Here, metals are always ready to release their electron, and non-metals are always ready to accept the electron. They only share when they do not see any electron that is being released for free. So here we are going to be looking into a transfer of electron from one atom to another. So we can call this electrovalent. Electrovalent or ionic bonding can be defined as a type of bonding where there is a transfer of electron from one atom to another. So we can perfectly say that electrovalent bonding is existing here if the following is attained. 1. If the atom transferring the electron attains its duplex or octet state by giving out all its valence electron to the atom that receives the valence electron to complete its shell, except the main transition element. It's only the main transition element we are going to accept from this idea. That is, whenever the atom is releasing its electron, the intention is that it must complete its octet state or duplex state. If it cannot complete its duplex state or octet state, it is not electrovalent. That is why hydrogen bonding with chlorine is not electrovalent, because when it gives out its electron, it will not look like any of the noble gases. 2. The atom giving out an electron is an atom with lower ionization energy, lower electronegative values, and low electron affinity. But the atom that is accepting the electron, or group of atoms that is accepting the electrons, must be one with higher ionization energy, higher electronegativity values, and higher electron affinity. Now, question would be, what do we actually mean by higher, lower, all these things? Okay, when we look at ionization energy is the energy required to release one loosely electron in a gaseous atom. That is what we mean by ionization energy. Now, when the energy is very low, it means that electron can be released easily, and mostly it comes from group 1, 2, 3. Group 1 is easier to release one electron in group 1, a little bit difficult in group 2, much difficult in group 3, but group 1 will always release it easily. Now, electronegativity means that that particular atom has ability to attract electron to itself. But if it is having a low electronegativity value, it actually means that it loves giving out its electron. Now, if it loves giving out its electron, it means that its electron affinity will also be lower. 3. The atom transferring electron is highly electropositive element, and the electron acceptor is a highly electronegative atom. And this highly electropositive element, we call them metals. Then the highly electronegative element, we call them non-metal. 4. It exists mostly between group 1, group 2, reacting with group 5, 6, 7 in the periodic table. So, group 1, group 2 bonding with any element would be ionic. It's not that I'm removing group 3, but I just want you to know that sometimes group 3 may fall our hand. For instance, if you look at aluminium is 1.61. If you combine it with 3.16 and you change the electronegative difference between them, it is going to be below 1.9, and any value that is below 1.9 in electronegative difference makes that thing to be only polar covalent rather than being ionic compound. So because of that, we are focusing more attention to group 1 and group 2 bonding with any of the non-metals. 5. The electron donor is mostly metal or ammonium ion, whereas the electron acceptors are mostly non-metals or negative radicals. 6. There is a high difference in electronegativity between the two atoms or species that combine to form the ionic compound, and the differences must be at least 1.85 or 1.9. So anything below 1.9 is taken to be a polar covalent compound, or we can even have it as just ordinary covalent compound. The last point here is that the electropositive metal, its ionic size will be lower than that of its neutral atom. This is because electrons are removed without removing proton. And whenever you do not remove proton and you remove electron, you see that proton will be more than electron. So that is pulling down of electron from the shell closer to the nucleus will be higher because protons are more than the electron. But if, for instance, you add electron without adding proton, the electron will start to have power to move away from the proton by repulsion or repelling. So according to what I wrote here, I say the positive ion ionic size is lower than that of the neutral atom because electrons are removed without removing the proton, which leads to a partial loss of one shell and a greater nuclear charge attraction towards the nucleus, whereas the negative charge ionic size is larger than that of its atomic size because electrons is or are added without adding any proton. So there is a reduced nuclear charge and increases repelling of electrons away from the nucleus by another electron, making the ionic size larger than that of atomic size. So what I'm trying to put up here is that if, for instance, we have oxygen, if oxygen gains 2 electrons, it is going to increase in 2 steps of electron. If it is fluorine that gains 1 electron, it's only going to increase in size by 1 step of electron. That means that oxygen forming ion, its size will be greater than its atomic size and also be greater than that of fluorine forming fluoride. I don't know if you get me on that. So let's look at a simple demonstration of metals and non-metal bonding. I'm using sodium chloride and potassium oxide, and that will be the end. But before that, I just want to give you the properties of these. 1, they are always crystalline solid with lattice. And 2, they have high melting and boiling point. 3, they are ions and not molecules. 4, they are good conductors of electricity in their molten form, fused form, or in their aqueous form. You have to know these properties of ionic compound. The last one is that they are mostly soluble in polar solvents. So let's look at sodium bonding with chlorine and potassium bonding with oxygen to give us sodium chloride and potassium oxide, and we are going to call it a day on this video. So we are going to have something that looks like this. You can notice that the shell shrink and you look as if the shell is actually lost, so the size of the ion is lower than that of the atom. I hope you get that for metals, but for that of non-metals it's actually going to increase. Let's try it out of potassium oxide involving potassium and oxygen. Potassium can only contribute to 1 electron, but this really needs 2 electrons, so we need to bring 2 potassium so that one of it will come here, the other one will come over here. So we will have, look at what happened here. This electron will be thrown to this place. I know I said there are times 2, so another of this potassium will throw electron to this place. So we will have something that look like this. This is a simple way of representing potassium oxide. See, ammonium chloride can actually form something that look like this, and I want you to try that. Thank you very much for clicking on this video. Don't forget to click on the share button and notification bell, and don't forget to share my link to your loved ones on your social media platform.